Hello viewers, welcome back to my channel. In today's video, we are going to learn in depth about what exactly are block ciphers. Well, block ciphers operate with a shared secret key between the parties. This key acts as the secret code that both the sender and the receiver should possess as the building blocks of your digital communication. This fixed size block ensures consistent and manageable encryption. So if the first ciphertext is 01010010 and the second ciphertext is 11110000. So this is nothing but your final ciphertext. Now let's move our attention to the various block cipher modes of operation. The first block cipher mode of operation is what we call as an electronic codebook. An electronic codebook is basically the simplest block cipher in which each block of plain text is independently encrypted with the same key. That is what we have seen so far. So if there are identical blocks in the input, they will produce the same output blocks, which can lead to certain vulnerabilities. This is one of the drawbacks present in the very first type, that is electronic codebook or ECB. So the use case is very simple. You can use this sort of a block cipher where we don't want a high level security or where we don't have a very confidential information in front of us. There we can use such kind of a block cipher. But if we have a highly sensitive information to protect, we should not or we should never go with ECB. Now let's see what ECB looks like. Fine, so this is the diagram corresponding to the electronic codebook. As you can see, it's the simplest kind of a block cipher. The first plain text goes into the very first block, that is this particular block, and the output is what we call as C1. So the plain text P1 is encrypted with the same key K, and we get the output C1. Similarly, the second block P2 is encrypted with again the same key K, and we get the ciphertext C2. This particular process goes on until we reach the last plain text and key pair. So at the end, we get C1.C2.C3 till Cn. These are nothing but the ciphertext corresponding to P1, P2 till Pn. The decryption again goes in the exact reverse fashion. Instead of the plain text as the input, now the ciphertext becomes the very first input for the first block. It is again treated with K as the key, and we get P1 as plain text. With C2, we get P2 as the plain text, again keeping the key K constant. This process goes on until we reach the last block where Cn is nothing but the input to the last block, key K remains same, and we get the output as Pn. So as you can see, it is the simplest kind of a block cipher mode of operation where the plain text is divided into the number of blocks, and each block is encrypted with the same key K. In the case of decryption, an exact opposite happens and we get the plain text back. So let's go back to the next kind of a block cipher, that is nothing but what we call as cipher block chaining mode. What happens in cipher block chaining mode is again very simple. Each plain text block is XORed with the previous ciphertext block before encryption. So this adds a little bit of security to the previous mode, that is the electronic codebook. So let's see how this works. This is nothing but what we call as a cipher block chaining or CBC mode. What happens over here is there is the introduction of a concept called as an IV or initialization vector. This initialization vector is nothing but it's quite similar to a random seed or a random matrix which acts as the first input to the block cipher. So what happens is this plain text, for example, if the plain text is of 64 bits, this IV should also be of the same size. Otherwise, we cannot XOR it, right? So what happens is these 64 bits of plain text are XORed with the 64 bits of IV, and we get the first output which goes inside this encryption block. Now let me clear one thing. This encrypt block is not the same for each and every algorithm. Different algorithms have their own set of functions. So this is just to generalize. Whenever we write encrypt, the functions which are present inside that encrypt block may be totally different from each other. It is just to symbolize that some operation is happening inside that encrypt block where one of the inputs is the key and the other input in this case is nothing but the output of the XOR operation. Clear? So what happens is that IV is XORed with P1 and then we get some result which is encrypted with K, key K, and we get C1 as the output. Quite simple. So this is the output of the first block. Now, as we saw in the previous case, all the different outputs were independent of each other in the first case, that is electronic code book. But in this case, each and every stage is dependent on the output of the previous stage. As you can see over here, the C1 is going as input to the XOR operation of the next block. That is, instead of XORing the plain text this time with the IV, we are XORing the plain text with the result C1 of the previous block. So this is how the cipher block chaining works. And the output goes into the encrypt function of the second block and the entire process continues. So this is how the final ciphertext is generated in the case of cipher block chaining. Now let's see how the decryption works. Again, the decryption is the exact opposite. While decryption, we have access to C1 and we are trying to obtain the plaintext P1. So what happens is C1 is taken as one of the inputs to the decrypt function. So we are basically going exactly opposite. So C1 is the input to the decrypt function. Using the same key K, we get some result, and that result is XORed again with the IV. The IV has to be known to both the sender and the receiver, then only the process can take place, right? So this IV is then used to XOR the result of the decryption operation, and as both of these are interrelated to each other, both the functions are interrelated to each other, we will get the same output as P1. We should get the same result as P1. If we are not getting it, there might be some changes or there might be some noise added during the communication process. Let's go back to the third type. The third type is what we call as a cipher feedback mode. So what exactly happens in a cipher feedback is, again, it's very simple. Cipher feedback is nothing but it turns a block cipher into a self-synchronizing stream cipher. Each ciphertext block, this is the important part of this definition, each ciphertext block is XORed with the previous ciphertext block to produce the new block of key stream. Again, read it. The difference lies over here. The previous one was each plain text block is XORed with the previous ciphertext block. Now what we are doing, each ciphertext block is XORed with the ciphertext block, previous ciphertext blocks. See the diagram carefully. What is happening over here is, as you can see, the initialization vector comes over here as the first input. Along with the key, it is encrypted, and we are getting some strange kind of output over here. What is this? S bits and B minus S bits. So initially what is happening, there is a initialization vector, assuming that the initialization vector is of 64 bits, for example. What happens is this 64-bit initialization vector is encrypted with another 64 bits of key, and we get some result. That result is further broken down into two parts, S and B minus S, where B is nothing but the block size. The block size is 64. For example, let's take S as 8. So this will be 8 and the remaining 56 bits will be B minus S. What is happening after the encryption process happens, out of those 64 bits, we are assigning 8 bits, that is the leftmost 8 bits, as the S bit and the remaining 56 bits as the B minus S bits. So what is happening? This S bit, that is these 8 bits, are XORed with the plain text 8 bits. If we are having a 64-bit ka plain text, we are dividing it into smaller fragments of 8 bits. So what is exactly happening is a block cipher is getting converted to a stream cipher. A stream cipher is nothing but each and every stream of data or each and every input of data is going through a different key. For each of these plain text, we are having a different value of key. For example, this is nothing but the key. So what I'm trying to do is I am XORing each and every bit of the plain text with a different key. That is what a stream cipher is all about. Whereas in the case of block cipher, we encrypt the entire block with the same key. So in essence, what we are doing over here is we are dividing the entire block of 64 bits of plain text into smaller fragments of 8 bits each. So assuming the block cipher is now behaving like a stream cipher. That is what we understood during the definition. So in short, we are having a 64-bit plain text, for example, and we are only taking the initial 8 bits as the input to the first block. So what is happening? Those 8 bits are XORed with the leftmost S bits, that is 8 bits in this case, and we are getting some output which is C1. So again, C1 will be of 8 bits only. Now what is happening is These 8 bits are then sent to the next block. Now what is this next block? We can see there is some different function happening over here. That is a shift register. What exactly is a shift register? Let me explain. Initially we had taken 64 bits of IV. If the IV is something like this, assuming these are the first 8 bits and followed by some other characters, right? So what happens is we are shifting these 8 bits, that is 1 2 3 4 5 6 7 8, we are shifting these 8 bits to the left. So the first value of this particular register will now begin from this. So what happens is we are shifting this register to the left by S bits. In our case it is 8 bits. So these 8 bits are discarded and we will get some blank 8 bits at the end, because we have already shifted this to the left by 8. So the last 8 bits, that is the rightmost 8 bits, will be blank. So we'll not keep that blank. What we'll do is, so whatever ciphertext we have got over here, that is C1, that will replace those 8 bits over here. This is a little tricky to understand. Again, I'm repeating. Whatever was the IV, that IV is shifted to the left by 8 positions. So the first 8 values, that is the leftmost 8 bits, are discarded. And whatever C1 we got, those bits will occupy the rightmost positions, because we have shifted this register to the left by 8 bits. Fine, so I hope you got the understanding. So now this shift register is again going through the same process and we'll repeat this until we get the ciphertext. So the exact reverse is what we call as decryption. We know that the IV is known to both the sender and receiver. So what we'll do is, the IV is again encrypted with K. The initial process remains same. S bits and B minus S bits. Now what we are doing is we are XORing those S bits, not with the P1. This time we are XORing it with C1, so that we get P1 as the result of first block. So I hope this process is clear. Again, what we'll do, again we'll take C1 and replace the shift register as we saw in the previous case. And this process keeps on going until we get the final plain text. With that, let's come to the fourth type, that is output feedback. If you see, in the previous case, we had taken only 8 bits of plain text and XORed it with the output of the encryption function. That is, we XORed P1 with S bits. But in this case, what we are doing is we are XORing the entire P1 with the output of this encrypt phase. So P1 is getting XORed with the entire output, that is of 64 bits, for example, and not 8 bits. In the previous case, we considered the block cipher as a stream cipher, but in this case, it will be considered as a block cipher only. So the entire plain text of 64 bits will be XORed with this output and will get 64 bit ka ciphertext. So what is different over here? The difference lies over here. Let me just clear these things up to make it easier to understand. The difference lies over here. As you can see, the output of this encryption phase itself is sent to the next block. Instead of sending the 8 bits ciphertext, which was used to shift the register by 8 bits, we are totally omitting that step and we are simply sending in the entire 64 bits output to the next phase. And this particular output is sent as feedback to the next phase. That is why it is also called as output feedback mode. And finally, the last mode is what we call as the counter mode. So what exactly is the counter mode? The counter mode is very simple. It turns a block cipher again into a stream cipher by encrypting a counter value for each block and then XORing it with the result of the plain text. See the diagram? Instead of the initialization vector, now we are making use of a counter. So what happens is the counter is nothing but a value. You can assume it as a timestamp, or you can assume it as a number, random number. So this counter value, how many bits it may be, for example 8 bits. So those 8 bits of counters will be encrypted with K again of 8 bits and will get some result again of 8 bits that will be XORed with the first 8 bits of the plain text. So the 8 bits of plain text will be XORed with the result of the encryption operation, which is again of 8 bits, and we'll get C1. In this case, what is happening, as you can see, there is no connection between the first block, second block, third block, and so on. So all these blocks are independent of each other and they can run at the same time also in parallel. So that is one of the advantage of using this counter mode. In the reverse is also possible. That is, during decryption, we are taking counter 1 as the first input. We are encrypting that, and this time we are XORing it with the C1 instead of P1, as we already seen in the previous phases as well. So that brings us to the conclusion of this pretty long video, where we have seen in depth how exactly a block cipher works in practice. So if you like the content of this video, do share it with your friends and leave your comments, your suggestions, your feedback in the comments box. So I would be really happy to bring new videos in the upcoming sessions as well. So stay tuned, stay connected. God bless you.